Okay. Huh. So we were doing solutions. How much of solutions do you guys remember? You start off and then we'll pick up from wherever you leave. Yeah. Tell me, what do you remember? What all did we do in solutions? On Smera?
I remember all those formulas like mass by volume percentage, molarity.
Okay, so we figured concentration of solution basically, like how do you express it, what they mean, all of that. Uske baad, we looked at solubility of solids and of gases, like mainly gases. Usme there's a little more analysis in that. So what do you remember? Solubility of gases, there was a relation that we figured. Arya?
This relation, like the pressure one.
Yeah.
Yeah, when you increase the pressure, the solubility increases.
Correct. So that was given, so that relation was given, it's called Henry's law. Sia, do you remember the mathematical representation, Henry's law ke liye?
X is equal to KH into the mole fraction.
XA itself is a mole fraction.
Oh, sorry, the PA.
So partial pressure is equal to KH into the mole fraction of that particular component. Sanskriti, what is KH?
Ma'am, KH is Henry's constant.
Henry's constant, yes. Okay. So that depends only on the nature of, yeah.
Miss, you told us last time that it's not X, right?
It's chi. Technically, it's chi. But as long as you guys know the concept, like you just know how to write it. Yeah. Okay. But yeah, that's a Greek alphabet chi. It's not like outright X. All right. So we're talking about Henry's law constant KH. So KH depends only on nature of the substance. Yeah, like intermolecular forces. What sort is it? Polar, non-polar. That gives the this thing. Like KH is a constant for a solute solvent pair, and KH also depends on the temperature. So solubility changes with temperature, right? So that's because the KH is modified. Okay. So we looked at all of that. Henry's law ho gaya. So we were starting with vapor pressure. So next thing we look at liquid-liquid solutions. So when you dissolve two liquids together, the point of interest, things that get altered, what we look at is it relates to the vapor pressure of both the liquids. Okay, so I think we like briefly discussed ki vapor pressure kya hota hai, all of that. Do you remember any of that? Yeah, anyone? Vapor pressure? All right, we'll start off from here. Okay, so what is vapor pressure is like, before telling the statement, I'll like explain what it is. So let's say you have a liquid, like we're not looking at any solutions abhi tak, purely just liquid, random liquids. Okay, so liquids have a tendency to evaporate, right? Like any liquid evaporates, like you have water, it dries up, evaporation hota hai. You have something like perfume and all also, like that evaporates, which is why you can like smell things. So the molecules get into the air, that's evaporation. So when you have any liquid, immediate space above it, so let's say this is the liquid, immediate space around it, like above it, yahan pe, you are going to have vapor molecules of that particular liquid. So when it is in gaseous state, like gases ka property hai, you have like volume, temperature, number of moles ke saath, like pressure is a characteristic, right? All gases exert pressure wherever they are. So specific pressure exerted by by the molecules of a liquid that have turned into vapor state. So that pressure is called vapor pressure. Okay, quite simply, that is it. So this is a completely natural phenomenon. कोई भी liquid हो, that's going to evaporate. अगर evaporate हुआ, converted to gas, and that gas exerts pressure. So specifically, उसका pressure will be your vapor pressure. So different liquids have different vapor pressures. So vapor pressure is affected, actually, definition. So this is the pressure exerted by vapors above liquid surface another important point, in equilibrium with the liquid at a given temperature. Okay, so why do we include this point is, again, a lot of factors at play here. Evaporation, sometimes it's fast, sometimes it's slow. And if it's like a solid just melted into liquid, or suppose it was in a container and then you just put it out, तो उतने सारे vapor molecules नहीं रहेंगे, right? So eventually, when it gets into that equilibrium where the rate of the liquid turning into vapor is equal to the rate of the vapor condensing back, when that equilibrium has been established, when this pressure like basically stabilizes at a constant value, so that pressure is what we consider to be the vapor pressure. That's all it is, like nothing else.
Miss, I didn't understand what you said in the last part.
So why do we
What
talk
did you
about equilibrium? So again, the pressure will keep fluctuating, right? Like imagine real world scenario. Let's say you just took water out of a container and put it in a cup. Or maybe like, or larger scale, imagine it just rained. So then the vapor pressure will not be so much, like there'll be a lot of fluctuations initially, like utne sare vapor molecules will not be there. So at that point of time, vaporization will be a lot more. But again, this won't continue on infinitely, because again, once the atmosphere, whatever the space is saturated with this liquid, फिर condense हो जाएगा. Like there's a lot of water molecules, they hit each other, and then one of it loses energy and it'll come back. So when the rate of evaporation is equal to the rate of condensation, when both these processes hit an equilibrium such that this pressure remains constant for those conditions at that particular temperature in those particular conditions. So that is the pressure that we consider it as vapor pressure.
Miss, but if the rate of condensation is equal to the rate of evaporation, मतलब net कुछ नहीं हो रहा है ना? Like
Exactly. Net कुछ नहीं हो रहा है. This pressure is constant. Okay. अगर like imagine if we are talking about water only, if the atmosphere was dry, then more water can evaporate. So tabhi this is going to fluctuate a lot. You're going to have, like if you want to measure specifically water vapor ka pressure amongst all the gases, that'll keep on increasing because water is still evaporating. But eventually at one point, this is going to stabilize because this is saturated with water vapors and condensation chalu ho jayega. So when both are equal, net kuch nahi ho raha hai and pressure is constant, stabilized at a particular value, that's when we say equilibrium has happened. So when the liquid is in equilibrium with its vapor, then when you measure the pressure, that will be the vapor pressure. Okay. Vapor pressure.
But when we say at, sorry, I'm so sorry. But when we say at a given temperature, it like for evaporation to take place, there has to be a certain temperature. Only then that particular liquid will get evaporated, right?
It can be any temperature. Like any temperature below the boiling point, evaporation will take place. If it is above the boiling point, पूरा boil होके पूरा gas ही बन गया. But any other temperature, like all the temperatures that it's in liquid state, evaporation will happen. And that is the reason, okay, now coming to the next point, why we say at a given temperature, that gets clear. So what the vapor pressure is, it depends only on two factors. One is it is affected by the nature of the liquid. And second, it is affected by the temperature. This is very easy, like you might have, like it'll be easy to make sense of this thing. Nature of the liquid, matlab kya? Some liquids can evaporate more easily than other liquids, right? Have you guys used like nail polish removers, right? So is that, like, in terms of evaporation and all, how would you compare it with water?
Faster evaporation.
Faster evaporation, right? So that's again nature of the liquid. Water is, you can intermolecular, like hydrogen bonding here, usme lots of very high intermolecular forces. It's a polar solvent. So it's difficult for the molecules to, let go of all the other molecules and go into vapor. But acetone, which is your nail polish remover, that's a lot more volatile. Like it's non-polar, it can easily get into vapor state. So that's what we mean by nature of the liquid. Nature of the liquid. So to figure it out, you look at the intermolecular forces, polarity, molecular mass, like how all of that stuff.
How does the polarity affect the volatility?
What are the intermolecular forces present in polar substances?
There's unequal distribution, right?
Huh?
In polar molecules, there's unequal distribution of it.
Within the molecules, unequal distribution of electrons hai. But overall, like intermolecular forces, do you guys remember we did this last year? Ek hai van der Waals hai, that's like present always. These are like London dispersion forces.
Yeah.
They're purely because of the mass of the thing.
Yeah.
इसके अलावा और क्या है? What all different types of forces do we have?
I just remember London forces. Other than that,
Anybody else? Like, do any of you remember intermolecular forces?
London
substances
forces.
में क्या क्या होता
I
है?
said London.
Polar substances में what type of forces do you have?
Dipole,
Yeah.
dipole induced dipole.
Yeah, there you go. You have dipole interactions. Then you have dipole induced dipole if it's like a mixture of one polar and some non-polar thing. And subse, like the most dipole on steroids is basically you have hydrogen bonding. Right? So Abhi, if you consider something like acetone, the only force at play is van der Waals. Maximum thoda, like because it has that oxygen, thoda dipole ho sakta hai, but not very much. But if you look at something like water or ammonia, usme van der Waals, dipole and also H bonding hai. Like a lot of like extremely strong intermolecular forces it has. Right? So that plays a picture in that plays a role in how easily can those molecules vaporize, and that in turn like affects kitne molecules vaporize hue, which will affect kitna pressure is being exerted. Okay. So that is one thing. So nature of liquid, intermolecular forces is at play here. So like based on what sort of intermolecular forces are there, that you'll end up with, okay, polar liquid, non-polar liquid, that sort of a thing. And the second force at play, like the second thing that affects vapor pressure is the temperature. So if you compare a hot liquid, cold liquid, which will vaporize more easily?
hot liquid.
Hot liquid, naturally. And why do you think it's the hot liquid that vaporizes easily? So
Like
this
the
relates,
molecules
yeah,
are in motion, so it's easier for them to escape.
correct. So this relates to the,
Latent heat of vaporization.
correct. So kinetic energy of the molecules. So higher temperature, matlab, they already have a lot of kinetic energy. So it won't take a lot for them to go into the vapor state. Like easily they'll vaporize. But cold one, like they need to get at that level and then they need to like they'll be able to vaporize. Okay. So intermolecular forces and temperature. So temperature is basically it's a direct relationship. Higher temperature matlab higher vapor pressure because more number of molecules are vaporized. And intermolecular forces के case में it's an inverse relation to the polarity. So higher polarity or higher intermolecular forces matlab vapor pressure will be less because it's like molecules are held on tightly by each other. They won't be able to escape easily. This is a direct relation. This is an inverse relation. What else do we know about? Yeah, so these are like basics of vapor pressure. Liquids here, so they will have a vapor pressure, and different liquids have different vapor pressure because of intermolecular forces at play. And vapor pressure will also change with temperature again because of the kinetic energy and all that. It's just like related to the rate of evaporation, basically. Now, when we come to solutions, so specifically we look at liquid solutions. Solid liquid solutions we have, but that's more theoretical. It's a smaller part, so we'll look at it later. Now let's look at liquid solutions.
Miss, could you show the previous one for
Yeah,
just a minute?
I mean, it's rough में लिखा है, so you don't. If you want, you can note it down for reference. Otherwise, you can.
Yeah, thank you.
Okay. Is everyone done? Let me know once everyone's ready. Then we'll look at solutions. Sanskriti, once you're finished.
Ma'am, I'm done. I've already done.
Okay. All right. So liquid solutions में liquid solutions मतलब एक liquid में you're putting a second liquid in there. So इसमें both solute and solvent are liquids. Okay. Now what do you think will happen to the vapor pressure? So one thing is there for sure. Liquid solutions में this is the glass. Let's say we are mixing a blue liquid and red liquid. Blue liquid है and उसमें we mixed some amount of red liquid. Because both of them are liquids, both the molecules will have a tendency to evaporate. मतलब इसके ऊपर we have red like solute के molecules भी है और solvent के molecules भी है, दोनों है ऊपर. So this is the liquid. Okay. Now, the total vapor pressure, I'll write it as, so the total vapor pressure will be equal to the partial vapor pressure of the solute plus the partial vapor pressure of the solvent. Make sense? क्योंकि solute भी है, solvent भी है. So solution का total vapor pressure जानना है मतलब like you add up the solute का vapor pressure and the solvent का vapor pressure. Okay. Now Now we have another law which dictates how do you calculate the partial vapor pressure of the solute and the solvent. So this brings us to Raoult's law. So just like Henry, Raoult also did some experiments. He figured. So mathematical expression for Raoult's law. So basically the partial pressure, the partial vapor pressure of a component in the solution, he said it is directly proportional to its mole fraction. Okay, this is the statement given by Raoult. This is Raoult's law. So basically when you have two liquids mixed which are in solution, the partial vapor pressure of a given component is directly proportional to its mole fraction. So what he's saying is, if the more of a solute you mix, more will its vapor pressure, more will its partial vapor pressure be. That's essentially what. That makes sense. Like if you have more of a substance, more of it is going to evaporate. Where uska partial pressure is also going to be more. That's what he says. So Raoult's law ka statement is, at a given temperature, again always these things we consider the temperature to be constant, because if temperature is variable, everything else changes. So at a given temperature, for a solution of volatile liquids, again, if the liquids are not volatile, if they don't evaporate easily, then there's no question of talking about partial vapor pressures and all that. So, yeah, Kavya.
Why didn't we take into consideration vapor pressure when we did solids in liquids and gas in liquids?
Gas and liquids, again, think of what vapor pressure is. One, consider solids and liquids. Solids का vapor pressure होगा क्या?
No, I know that solids and gas, like solids won't have, but solid is in liquid, ना तो उसका तो vapor pressure होगा ना.
Hoga, yeah. So we just took liquid solutions because it's a little more complex. Solids and liquids is simpler. So once we're finished discussing this, then we look at solids and liquids.
Same with gas and liquids, right?
Gas and liquids, the concept and all will be the same. And gas ka, we already have Henry's law for the solute part of it. Like gas ka partial pressure jitna hai, that's directly proportional to its mole fraction in the solution. So it's very adjacent to that concept. Okay. All right. So for a solution of volatile liquids, the partial vapor pressure of each component is directly proportional to its mole fraction present in the solution. Okay, that is. Okay. Again, this is pretty straightforward. It's just this little thing put in multiple words. So at a given temperature for a solution of volatile liquids, since they're volatile liquids, we know that both the components are going to have definite vapor pressures. So the partial vapor pressure of each component is directly proportional to its mole fraction present in the solution. So each component's partial pressure is directly proportional to uska mole fraction. So whichever is in higher proportion will dominate vapor pressure wise also, basically. That's what it's saying. Quantity wise. Right. So once you guys have finished writing the statement, we'll do the derivation of the mathematical formula. Arya is writing. Siya, Sanskriti? Sanskriti is done. Okay. Siya, let me know when you're done. Then we'll. Okay. Okay, Arya, once you're finished, we'll do it. Done? Okay. Cool. So what did Raoult's law say? Suppose solution may we have two components, component 1, component 2. Let's just call it 1 and 2. So partial pressure of the first one is directly proportional to its mole fraction, and partial pressure of the second one is directly proportional to uska mole fraction. Okay. Now, if we were to remove the constant of proportionality here, it is found out that the partial pressure will be equal to P01 times mole fraction of 1. And partial pressure of the second one will be P02 times mole fraction of 2. So here P01, P02 are, so P01, okay. So P0 represents the vapor pressure when it is alone in the solution. Like P01, if the mole fraction was equal to 1, मतलब और कोई component नहीं है. So suppose we are looking at a mixture of water and what other liquids can you put in water? Like let's say HCl. So when it is purely water, uska vapor pressure will be P01 of P0 of H2O. When it is purely HCl, P02 is uska vapor pressure. Okay, so that's what P0 represents. P01 and P02 are pure vapor pressure, like vapor pressures of the components when they are pure. When they are not mixed with anything else. It makes sense, right? Mole fraction, like suppose component ka 1 hai, like 1 out of 1, like the whole, all the moles belong to component 1 only. Then P1 will be equal to P01. That way. Now, P total, so this is total vapor pressure solution ka. Please remember the law of partial pressures. If you had to find total pressure of like a mixture of gases, that will be equal to sum of
the partial pressures.
sum of the partial. So T total will be equal to P1 plus P2. And if like again, because it's a mixture of gases, it'll be very difficult to measure what the partial pressure of each gas would be. So instead, P1 के place में you can figure out P1 naught into chi1 plus P2 naught into chi2. Just substituting this one here. Also, again, it's a mixture of component 1, component 2, right? So also we have chi1 plus chi2 will be equal to 1. Mole fraction hai. If we have two components, then the total should be equal to 1. Fraction of the first one plus fraction of the second one. So we can substitute it. So that will be equal to x2, this one. So this will be P1 naught into x1 plus P2 naught into 1 minus chi1. So just rearrange it. You'll get P2 naught plus P1 naught minus P2 naught x1. Similarly, you can also write it in terms of P1 naught also, like instead of mole fraction of component 1, if you have the mole fraction of component 2, then just write mole fraction of component 1 equal to 1 minus mole fraction of component 2, and accordingly these P1, P2 iska values also will change. Okay. So essentially, if you know the concentration of the solution, like mole fraction kitna hai, either the component 1 or component 2, and if you know the individual vapor pressures, then you'll be able to figure out what is the overall total vapor pressure of the solution. And other way around, like suppose you have a solution and you know what is the total vapor pressure of that solution, but you don't know how much of solute is mixed in it. So if you know the individual vapor pressure at that particular temperature, you know the total vapor pressure, so you can get the mole fraction of any of the components using this thing. Okay, so that's what Raoult's law is used for.
This
So
derivation.
yeah, so this is the derivation from the Raoult's law ka statement.
And the P naught values will always stay the same, right?
Yeah. Always मतलब एक temperature के लिए like water at 35 degrees Celsius, उसका vapor pressure will always be the same if you have pure water. So again, just like with Henry's law, we have a formula. इसका related एक graph भी है and some analysis based on that. So once we finish that, we'll do a couple of questions based on this thing. So go through it. Like if there's any point where you're not able to make sense of it, if you have any questions, we'll discuss that. Otherwise, we'll move ahead. Okay. Should I go to the next part?
1 second.
Okay.
what did you do in the third last step? Yeah, no, उसके नीचे.
ये वाला. Just rearrange it. So P01 x chi1, P02 minus, like open the brackets, then take P2 on this side and take x1 common, and then you get this. Just rearranging mathematics. I'll say that.
But it will be P0 to chi1, right? So where is that?
P02 chi1 इधर से आएगा.
Yeah, so like where did we write that?
यहाँ पे chi1 कॉमन लिया तो P01 minus P02 हो गया. So expanding this, we get P1 naught chi1 plus P2 naught minus P2 naught chi1. So P2 naught अकेला जो है, written it here, and from this and this I took chi1 common. तो bracket में P1 naught minus P2 naught आ जाएगा.
One.
Okay. Sanskriti? Done?
Yes, ma'am.
Sanskriti, you there?
Ma'am, I'm there. Can you hear me?
Yeah. Okay. Are you done? Like, should we go to the next part?
Yes, ma'am, I'm done.
Where's your video? What happened?
Ma'am, actually your voice is coming lower, so I tried switching off my video for a while.
Okay. Okay. All right. So some conclusions based on the Raoult's law formula. So one, we figured that total vapor pressure, we can figure out the total vapor pressure. It can be related to the mole fraction of any one component. So you don't have to find both of them. Again, it's pretty self-explanatory because mole fraction is like a fraction of moles. दूसरा component का if you do 1 minus that मिल जाएगा. So you can basically get it from, if you, as long as you know the mole fraction of any one of the two components. Another thing we can see is the variation is linear, just like Henry's law. Let me write that again here. Makes sense. So P total will be equal to P02 minus P1 naught minus P2 naught times mole fraction of 1. So if this is a variable and this is obviously as long, like as you change the concentration, the total vapor pressure is going to change. So if you look at the relation between these two, the variation is linear. So it's like y equal to m into x plus c. Linear equation जैसे हो गया. And the third point is the total vapor pressure can increase or decrease with increase in the mole fraction of component 1. Okay. Here. Okay. What does the statement say? Read it a couple of times and tell me if you guys can understand this. क्या बोल रहे हैं इससे?
How increase or decrease? You increase.
So if you had to figure out the relation between the total vapor pressure and the mole fraction of like any of one component, can you for sure say whether it's like, oh, it's directly proportional or it's inversely proportional, is it?
It also depends on how much of component one is in solution.
That's what we're trying to figure out. It depends on how much it is. So is that relation, like, is it a direct relation or an inverse relation? Like, can you say for sure, for a fact, that if I increase the concentration of this component, तो मेरा total vapor pressure भी increase होगा? Can you say that?
Yeah.
You can. Okay, Sia is saying yes. So फिर why am I saying increase or decrease? What is the catch here? Again, this is more mathematical. Like, think of it in those terms.
If P2 is greater or P1 is greater.
Exactly. So the mole fraction is multiplied by P1 naught minus P2 naught, right? So if P1 naught minus P2, like if P1 naught is greater than P2 naught, अगर P1 naught का vapor pressure ज़्यादा है, मतलब this is a more volatile liquid, like आसानी से vaporize हो रहा है. Then as long as you keep, so this minus this overall positive value रहेगा. So as long as you keep increasing the fraction of component 1, total pressure भी increase होता ही रहेगा. Right? So this is multiplied by this. But if it's the other way around, if P1 naught is less than P2 naught, what will happen to this difference?
Negative.
Negative हो जाएगा. So if I keep increasing the concentration of like component 1, so minus of something into that concentration, तो ये पूरा term will keep decreasing, which means that P total will keep decreasing. Yeah.
But you're adding P0 2 also, right? So if P0 2 minus, like if that is negative, even if you're adding.
But ये तो
So-
constant है ना, like all the things with naught are constant, क्योंकि that's the pure vapor pressure. Okay, so this is not changing. So I'm adding, so I'm getting something like if P2 is 75, I'll get 75 minus some value. So if this value keeps increasing, so 75 minus 10, 75 minus 20, the overall keeps decreasing. Right? So even though I keep increasing X, like the mole fraction, my total vapor pressure keeps on decreasing. So basically, this relation, whether it's direct or inverse, like total vapor pressure increase होएगा कि decrease होएगा, if I keep increasing one of the components, that depends on the individual vapor pressures के साथ. So it can increase or decrease. The main dependency is it depends on the vapor pressure of pure components 1 and 2. Okay. So if I'm increasing the concentration of the more volatile substance, the overall vapor pressure increase hoga. But if I'm increasing the concentration of the less volatile one, like jiska vapor pressure kam ho, then overall vapor pressure will keep decreasing. That's what this thing is. So solution ka vapor pressure, it's not a simple relation with the concentration. It also depends on like the nature of each of the components, which is more volatile, whichever is less.
Miss, I didn't understand the third point at all.
Okay. Okay, let's like, have you finished noting everything down? 3 points? Okay. Let me write this properly, clearly here. So we have P total is equal to P2 naught plus P1 naught minus P2 naught times chi 1. ये derive किया ना? This is the formula we have. Okay. So the third point is trying to tell you what is the relation between individually, like total vapor pressure on the concentration. Like अगर एक component का concentration, if we have increased it, then what will happen to the total vapor pressure? Can we say for a fact total vapor pressure absolutely will increase, or can we say that total vapor pressure will absolutely decrease? ऐसा कुछ बोल सकते हैं?
We can say direct relation, no?
It looks direct. The issue comes कि the concentration is multiplied by this thing, P1 minus P2. Okay, so P1, P2 are individual vapor pressure of the pure components. Like if we have only one, फिर उसका vapor pressure क्या होगा? If we have only two, उसका vapor pressure क्या होगा? Okay, so consider two cases. Like case one, if P1 naught is greater than P2 naught. So P1 naught greater than P2 naught मतलब P1 naught can easily vaporize. इसलिए उसका vapor pressure ज़्यादा है. So there's more quantity in the gas form. So if P1 naught is greater than P2 naught, तो ये brackets में जो है इसका value what will it be? P1 minus P2.
What?
So when P1 naught is greater than P2 naught,
Yeah.
P1 naught minus P2 naught be equal to, like, what sort of a value? will it
Positive value.
Positive value, right? So
Yeah.
positive value multiplied by this concentration, तो P total क्या होगा as you increase chi1?
It'll increase.
It'll increase, right?
Yeah. Yeah.
So in this case, so P total is directly related to the mole fraction of that particular component.
Yeah.
Flip side, if P1 naught is less than P2 naught,
Yeah.
फिर इसका वैल्यू क्या होगा?
Negative.
ये पूरा नेगेटिव होगा. So if this is
Correct.
negative, as you increase chi1, as you increase the mole fraction of 1, total P total क्या होगा?
But you don't know if P02 is a positive value or not.
Vapor pressures are always positive values, no? Negative pressure कैसे रहेगा?
Yeah. Same.
Yeah.
But then how can you say that if you increase? Wait, let me think.
Purely mathematical. Like सारे positive values ही है. Mole fraction, like number of moles negative नहीं हो सकता है. Vapor pressure negative नहीं हो सकता है क्योंकि it's the pressure.
But difference हो सकता है ना अगर P2 बड़ा है.
Negative हो सकता है. Exactly. So अगर P2 बड़ा है तो this difference is negative. So basically we have P total is equal to some positive value minus, like some positive value minus some number, like difference jitna hai, that number times mole fraction. Okay, so in this situation, as you keep increasing the mole fraction of this component,
तो
so
value कम होता जाएगा.
yes. Yeah. So total vapor pressure, it may increase or decrease as, okay, this I've put it the other way around. So in both the cases, I'm increasing the concentration. So total vapor pressure, it may increase or it may decrease with increase in component 1. So we can't say that for sure. it depends on the vapor pressures of the pure components. So अगर P1 बड़ा है तो it is going to increase, अगर P2 बड़ा है तो it will decrease. That's what the third point says.
Yeah, thank you.
Okay, no problem. ठीक है, guys, come back, rest of you. Yeah. Okay, the next thing is graph. Now, because we are dealing with P1 and P2, दो components है, दोनों के vapor pressure है, graph will be slightly different. So इसमें we will consider two y-axis. Okay, just gonna adjust this. Okay, so x-axis पे we'll take the mole fraction. Okay, so leftmost point, mole fraction of component 1 equal to 1, and mole fraction of component 2 is equal to 0. Matlab, at this point, so like in that container, we have only component 1 and none of component 2. And rightmost point, it's the other way around. Mole fraction 1, 0 of component 1, and we have purely component 2. So in the middle, it's basically, as component 1 decreases, component 2 increases. So halfway point is like equal, like this is also 0.5 and this is also 0.5. That's how this particular graph is. So
This graph is what we just did.
huh? Yeah. Abhi jo,
Increase or decrease that.
yeah. Okay. So when it is purely, so on the y-axis, we will consider the partial pressure. Okay. So when it is purely component 1, vapor pressure will be of pure component 1. So let's say it's somewhere over here. So this will be P1 naught or P naught of 1. And when it is purely component 2, vapor pressure also pura like component 2 ka hi partial pressure hoga. And that when you mix both of them, the total vapor pressure, it ranges from P1 to P2. ऐसे रहेगा the graph. So individual vapor pressure, we'll draw it in this thing. So component 1, when it is purely component 1, maximum itna रहेगा. When there is 0 of component 1, it like you won't find partial pressure be 0 रहेगा. So component 1 ka pressure will vary this way. Component 2 ka partial pressure will vary this way. And total vapor pressure is the solid line. Okay. Yeah, Kaveri.
This we're assuming that P02 is greater than P01.
Yeah. If it's the other way around, फिर line
Go
is.
back to the previous slide, just 1 second. So इसमें तो minus होगा ना फिर minus whatever I1.
Yeah.
So it will be decreasing.
Yeah. So as you keep increasing concentration of component 1, as the mole fraction of component 1 increases, so when you're going this like this way, you can see that the pressure is constantly decreasing. So if P01 was greater than P02, then graph like it'll reflect put it in a different color. So P01 ka agar itna hai or P2 ka itna hai, so then the line also will become this way. But basically, solutions ka partial pressure, like vapor pressure and all, this is how they are denoted. Like this is what the graphs usually look like. So दो y-axis है, one of the axis corresponds to component 1 and the other one corresponds to component 2, and all the space in between covers all of the concentrations. Okay, because this is purely 1, this is purely 2. So depending on where you are on the x-axis, that will denote, okay, what is the ratio of 1 to 2, like mole fractions kitne rahenge. And y-axis pe all of these points correspond to the total vapor pressures. Okay. So description, yes. So the dotted lines represent the individual partial pressures, or let's say partial pressures of each component. So this is the component 1 का partial pressure, and यहाँ पे जो है, this is component 2 का partial pressure. So when it is purely 2, it is the proper partial pressure of component 2. When it's purely 1, partial pressure of component 1. And another thing you can see is the minimum value of P total is equal to the P naught of less volatile substance and maximum value of P total the partial, like the vapor pressure of more volatile component. So basically, like if you have a solution, like if you take a pair of liquids, unka total vapor pressure, it can't be any random value. It will always range from the partial pressure of the less volatile to the partial pressure of the more volatile substance. उन दोनों के, like if you take the total of both of them, it is going to be somewhere between those two values only. It won't fall outside those values.
Where the dotted lines are meeting, what's the significance of that point? Significance of that point? Yeah.
यहाँ पे, so basically, so if you want equal vapor pressures on from both the thing, you can figure out at what concentration are you going to have equal quantities in the vapor phase for both.
So P1 is equal to P2.
Yeah. So this is the point where P1 equal to P2.
So ma'am, that be at the point where Chi1 and Chi2 are 0.5?
Not necessarily, no. Like you can see here, 50%
It is necessary because like
towards this.
no, but like P1 is equal to P01 into Chi1, and then P01 obviously remains the same. So Chi1 and Chi2 both have to be 0.5 for us to get P1 and P2 equal, right?
No. We'll do this mathematically. Wait. So you want P1 equal to P2, right? Which means,
Yes, after writing this, can you go
huh.
to the previous?
Yeah, finish off noting this down, then we'll discuss that part. Sia has done. I saw that. Smera is also finished. Okay. Sanskriti, let me know when you're done. Okay.
Ma'am, I'm done.
Okay. Okay. Kaveri is also. Arya is also done. Okay. So, all right. So you want vapor pressures to be equal, like gas phase mein, which means P1 naught chi 1 will be equal to P2 naught chi 2. Are P1 naught and P2 naught equal, Kaveri?
No.
तो फिर chi 1 chi 2 equal कैसे रहेगा?
It can be, no?
So if chi 1 and chi 2 are equal, if you want to get 0.5 0.5, वो cancel okay, then P1 naught should be equal to P2 naught.
So what is the at that point where the partial pressures are equal, what does that depend on?
That depends on P1 and P2.
So it's like any random point.
Yeah, it depends on what substances you take.
Yes, but for P1, P2 to be, sorry, P1 not P should be equal, then it should be the same fluid. Now, only then the both in pure component, the values would be the same.
It may be pure, it may be two very similar fluid, like liquids also. Can't say for a fact. Matlab, so many
But
different.
at a constant temperature, most likely is it to be
Yeah.
the same fluid.
Yeah, it can come very close, but yeah, again, you can't say that for sure ki like same ही रहेगा. Yeah. Okay. Now there's a third point. This is very, very important because this will lead to, like, this can be very, very confusing also. So the composition of vapor phase can, like, in equilibrium, like matlab, when the solution is in equilibrium with its vapor phase, can be determined by, it can be determined from the partial pressures that you have as Pi equal to Xi into P total. अभी यहाँ पे जो मोल फ्रैक्शन बोल रहे, बात कर रहे, this is the mole fraction in the gaseous phase. This is not to be confused with the mole fractions your denominator में. This is a completely different equation for a different situation here, this particular formula. Yeah. So Raoult's law say the P total we are talking about is derivation में जो, like, the what we are talking about is, so the total partial pressure in the vapor phase is equal to partial pressure of the first component times the mole fraction of the first component which is in solution. And यहाँ पे what we are talking about is, now this is the P total, this particular P total, and we want to know P1 kitna hai. Like vapor phase mein, what is the partial pressure of component 1? You can figure it out based from Raoult's law, and using that you can figure out what is the mole fraction in the vapor phase. So this particular mole fraction represents the mole fraction of the gas in the vapor phase, in the gaseous phase. This is not the concentration. Okay, so this is like when you were doing Dalton's law of partial pressures. Remember, like the partial pressure of each component is equal to fraction of that component times the total pressure. So that is the formula we are applying over here. Okay, so it'll get clearer when we discuss questions. But yeah, just wanted to, when you note this down, it will be less confusing. Like don't confuse this with the mole fraction we were talking about earlier. This is different from that. Okay. Okay. So once you finish with this, we'll do a couple of questions, and after that we can go to the next concept. So that is it for liquid-liquid solutions. This is the main thing, and we have further applications of this. Solutions that don't follow this line cleanly. You have ideal and non-ideal solutions and all. But as far as the quantitative analysis goes, this is the main thing about liquid-liquid solutions. What happens with the partial pressures and all that. Okay. So let me know when you guys are ready for a numerical. We'll do an example problem.
Can you go to the next page?
Yeah. Next page mein aur kuch nahi hai. Like this, I was just showing how agar partial pressure is equal hai, it doesn't mean that the mole fractions are equal. So Kaveri, what you are talking about is gas phase mein, if the number of moles are equal, then the partial pressures will be equal. In case of Raoult's law, it is not, like we can't say that because this represents the mole fraction in the solution, like the concentration of the solution. That's where the difference is coming. Okay.
I didn't get it. What?
So you were saying, like, you had a thought key if the partial pressures are equal, ਫਿਰ mole fractions also should be equal, right? So this is the case in the vapor phase.
In vapor phase.
Like if you look at only gases, अगर number of moles equal है तो उनका partial pressures भी equal रहेगा.
But in liquid also it is possible for them to have 0.5, 0.5.
It is possible, but अगर liquid में 0.5, 0.5 है, तो it is not necessary कि उन liquids के vapor pressure भी equal रहेगा. So the vapor, like the mole fractions in gas phase are different from the mole fractions in the liquid phase. So both of them will not have the same relation with the partial pressures.
And now also, we usually say that the solvent is higher in amount than the solute, right? So if the mole fraction of both is 0.5, 0.5, how do we know which is the solvent and which is the solute?
Then you, like, either of them you can classify as solute and solvent. Like we can't say for sure. That's why when it comes to, like, we use solvent, solute less and less, and that's why we start talking about like component 1, component 2, and we talk about it in terms of mole fraction. So that gives us more flexibility of not restricting it to solute, solvent.
Could you go back to like the last slides for a second? I missed the last one.
This one.
Okay. Is the P1, like the formula you wrote abhi last mein, that can only be used for gaseous phase? Right?
Yeah. Usme all the variables we're talking about, mole fraction, partial pressure, all of that relates to the gas phase only. Nothing in relation to the concentration and in which state.
Done.
Alright, do an example. Okay. So, so the vapor pressure of ethyl alcohol at certain temperature is 20 mm of Hg. Its mole fraction. So this, okay. So what does the first statement give you? Vapor pressure of ethyl alcohol at 298 K is 20 mm Hg. मतलब is this P1, P01 like क्या है? What is 20 mm Hg?
P01.
Correct. So P0 of ethyl alcohol is given as 20 mm Hg. Okay, so vapor pressure of pure ethyl alcohol is what they mean here. Okay, now its mole fraction in a solution with methyl alcohol. The solution may we have ethyl alcohol and methyl alcohol. So dono, it's mixed in a ratio such that mole fraction of ethyl alcohol is 0.4. Matlab, baki 0.6 is methyl alcohol, but we don't need that right now. What is its vapor pressure in the solution if the mixture obeys Raoult's law? So P of C2H5OH क्या है? इसका vapor pressure क्या है? If it obeys Raoult's law, so you can like directly apply Raoult's law without any problems. Okay, so can you guys work this out and tell me what it is? अभी formula भी लिखा है based on Raoult's law. What should it be? Sanskriti, see, are you guys working it out? I can't see you also. What's going on? Ah, nice. Kaveri already solved it. Kaveri got it. Like rest of you, इतना time क्यों लग रहा है? It's pretty direct question. Sanskriti, either.
Yes, ma'am, I'm here.
You solving this?
Yes, ma'am, I'm doing it.
Okay. Arya also got it. Pretty straightforward, no? Like question में ही दे दिया what you're supposed to use. Says mixture obeys Raoult's law. Like what else we use? Direct Raoult's law का formula. Sia got it. Smera got it. Nice. Okay. Sanskriti, where are you? Like where have you reached? You getting this? Sanskriti, you there?
Yes, Ma'am, just a minute, I'm saying.
Are you getting it? Like, where are you sending? Or you can even tell your answer, like everybody else has done, so we can discuss this.
Ma'am, I'm not sure,
So Raoult's law, you just wrote it, right? What does Raoult's law state? Formula क्या है Raoult's law का?
ma'am, the first one that we wrote or the second one? The first one was P1 not dot x1, that is multiplied by x.
What does it equal? Like P naught into the mole fraction, what does it give you?
Ma'am, that is 8.
A.
Just a second.
No, I can't. Like, did you say 8 or A? What is it?
Ma'am, 8. I said number 8.
हाँ, like ठीक है, you multiplied 20 times 0.4, that is 8 mmHg. But what is this essentially? Like number 8, what is it? Multiply करके क्या मिला?
And that is P1.
That is P1, yes. And that's what you're supposed to find out.
Okay, I did correct. I was not sure.
Matlab, like you haven't, like, you know the formula, but you haven't understood what it stands for. Okay. So Raoult's law states that vapor pressure in the solution, हर एक component का vapor pressure, which is your P1, in this case PC2H5OH, क्योंकि हमें पता है component 1, component 2 क्या है. So vapor pressure of that component is equal to the mole fraction multiplied by उसका अगर वो pure component रहता है P naught, तो तभी vapor pressure, like once you multiply both of these, that will give you the vapor pressure in solution. ठीक है? Right. See if there's another question. Oh, nice. Okay. NCERT type question. So the vapor pressures of pure liquids A and B, now we have A and B, are 450 and 700 mmHg at this temperature. Find out the composition of the liquid mixture. मतलब हमें mole fraction पता नहीं है. We don't know the concentration. If the total vapor pressure is this, so we have P total. So first finish till here, uske baad we'll see, like if you can do it, do the composition in vapor phase. Otherwise finish till here, then we'll discuss this. Take a couple of minutes. 4:25. Has everyone started working it out?
Yes, yes.
Okay. if anyone is stuck, not able to figure out how to proceed, let me know. Otherwise, continue solving. And in case you don't know how to proceed, always start with given. So figure out what is given here. You given some values 450, 700, figure out what they are, 600 kya hai. And then find like what are you supposed to find. Then see what formula you can apply.
Is temperature of any relevance here?
No, but it helps that, okay, at a given temperature, that temperature is constant. Numerically, it's not of any relevance, but conceptually, again, as I said, vapor pressure will change with temperature. So at 350 K, you know that, okay, itna hi rahe. Smera already got it, okay? Let's see. So this is composition in the solution, right, Smera?
Yes, ma'am.
Okay. Are you also finding composition in vapor phase?
I'll try. I'm not sure how to proceed.
Again, as I said, like last step में हमने discuss किया ना, you know the individual vapor pressures, you know the total vapor pressure. So now you have to find out the partial vapor pressure, and वहाँ से you need to figure out the composition. Okay, it's slightly longer. We'll discuss. Try it out if you can. Otherwise, we'll do it. I'll do it here on the.
Okay.
Sia also got it. Smera, Sia, both of you got the same answers. सही है. Guys got the right answer. Only two people have done it. Arya, Kaveri, Sanskriti, where you guys at? क्या हो रहा है?
I'm not set.
Setting, ठीक है. Oh, Sanskriti, I think decimals or somewhere there's. Just check your calculations. Beach me, you missed out on. Kaveri got it. ठीक है, सही है. Yes, Kaveri got it.
Vapor phase, I don't understand. Vapor phase wala, I don't know how to do.
Okay.
Yes.
Sanskriti. Okay, we'll do that on the board. In the meantime, Arya, are you sending? Like, have you sent already or yet to send?
No, ma'am.
Okay. And Sanskriti, can you tell me how you did this? ये थोड़ा सा अलग आ रहा है. So I want to see what happened there. Calculation error है या conceptual है? I wanted to check. So Sanskriti, one way you can figure out if your answer is right or wrong is you're figuring out the composition, right? मतलब mole fraction है, and mole fraction always उसका range होगा 0 to 1 because it's literally a fraction. Like is it 0.5, 0.6, 0.25, that way. So figure it out. Okay, Arya also got it. Ha, Sanskriti, tell me what you did. What is given in the question? We'll start with that.
Ma'am, total is given as 600.
Okay, P total is 600 mmHg. What else?
P1 naught is given as 450.
Yes, that is P1 naught is 450. Let's call it A and B because यहाँ पे they've outright given A and B. आसान रहेगा.
And PB naught is given as 700.
Yes. Okay, next. You're supposed to find like basically mole fraction of A and B.
So I use the formula P total equals to PB naught plus into bracket P1 naught minus P2 naught x1.
Huh. X like chi A, mole fraction of A. So solve this, you should get chi A. मतलब calculation में error हुआ है. So check that. So when you solve this, you should get chi A equal to 0.4, not 400. Okay. So chi B, like it's a mixture of A and B. So mole fraction of B will be 0.6. Okay. यहाँ तक pretty much everybody has gotten it. Sanskriti, like note down these values and focus. We'll figure out
Ma'am,
composition.
I found my mistake. I by mistake added it. I had to divide it. I added the value.
Yeah, okay, good. So anyway, you got this. Now composition in the vapor phase. So let's see how we do that. Example 2 है. All right, so right now we have P naught A is 450 mmHg. P naught B is 700 mmHg. We have P total equal to 600 mmHg. And we got composition. So in solution ka composition is mole fraction of A is 0.4 and mole fraction of B is 0.6. Okay, so this is the situation. Okay, दोनों का solution है. Vapor phase में how much of A, how much of B, we don't know that. But can you figure out the partial pressure of A and partial pressure of B? So this is in vapor phase.
Yeah, we can just multiply.
Correct. तो बताओ PA PB कितना होगा?
450 into 0.4.
हाँ तो कैलकुलेट करके बताओ ना.
180.
Yeah.
Yeah, 180.
And PB
420.
420. Okay. So we know, okay, so partial pressure of A is 180, partial pressure of B is 420, और दोनों मिला के total should be 600, which it is. So from this information, can you figure out what is the mole fraction of A in gas phase, in the vapor phase?
Would it be like 180 upon 180 plus 420?
There you go. That's exactly it. So 180 upon 600. And similarly, you can figure out mole fraction of B in vapor phase also. 20 upon 600. Calculate कर लो, मिल जाएगा. 6 3s are 6 10s are 3 by 10. This is 0.3 and This will be outright 0.7.
Can you explain after in vapor phase?
Yeah, absolutely. Can you guys switch on your video? Okay. So for this part, now we are focusing only on the vapor phase. So you need to remember the concepts related to gases that you guys did pehle, with ideal gas laws and all. So it's basically a mixture of gases. We have two gases, A and B. A ka partial pressure is this much, and B ka partial pressure is this much. We have total partial pressure A and B, like P of A plus P of B. P total is 600, or you can get it by adding 180 plus 420 also. So when you have a mixture of gases, what is the relation between all their partial pressures and the total pressure?
They have given 180 and 420.
No, you found this out from Raoult's law again. So partial pressure is equal to mole fraction of A times the like this into P naught of A.
Yeah, okay.
So this will be equal to, like, why do we have 600 is can write down. So here we use the concept P total in gases is equal to mole fraction of A into PA. So rearrange this a little, mole fraction of A will be equal to PA times P total. So this is what I was talking about. Yahan pe in this relation, this mole fraction is basically for the vapor phase ka mole fraction. This has no relation with solution ka concentration. That's why I've treated this as a separate thing, like exclusively in vapor phase. Think of it, we have two gases A and B. दोनों का individual like partial pressures पता है, total pressures add करके आ जाएगा. So how do you figure out the mole fraction from this information? Okay. Arya, Kaveri, Sanskriti, you guys clear?
Yes, ma'am.
Kaveri?
Yeah.
Yeah.
So first we find PA, PB, then to find XA in vapor phase, we find out so we divide the 180 what the total pressure.
Yeah.
And similarly for B.
Yeah.
And where in the notes have you mentioned P total is equal to chi PA?
This one. यहाँ पे.
Oh. Just a second, I'm going to write that.
That's why specifically is the point, like composition of the vapor phase. This is like using that again, partial pressures concept of gases is how you can use it.
What is I in that?
I is like component, like P1 hoga to chi1, P2 hoga to chi2.
The gaseous phase and vapor phase is the same thing, right?
Yeah.
Done.
Yeah. Okay, I'm just looking for more questions. You guys get a little comfortable because iske baad pura theory hai. This is the main numerical part of this thing. Look at question number 3.
Miss, could you show the first one? No, previous one.
Previous one. This part, this one.
Yeah.
Huh. Is there any part you didn't get, Arya?
No, I don't.
So लिख लो ना, like just do it on your own. Why do you want to copy? Like, क्या हुआ?
Yeah, thank you.
No, but honestly, like, what did you want to copy or note? Like, was there any part you were confused?
No, I just saw that I didn't take down something, some statement or anything that you didn't write.
Acha, ठीक है. Presentation basically. Okay. Question number 3. So vapor pressure of pure A is 70 mmHg at 25 degrees Celsius. It forms an ideal solution with B in which the mole fraction of A is 0.8. The vapor pressure of the solution is 84 mm at the same temperature. The vapor pressure of pure B is how much? Right. Take down all the information you have, and then it becomes very easy, you know, like what to use and how to apply. Smera already got it done. Nice. So once you're done with 3, look at number 4 also. Like do 3 and 4, and then we'll go to the next thing. Arya also done it. Okay, both of you got different answers. Now I'll have to check. Arya, it cannot be. So
It cannot be.
technically, you're
Yeah.
doing both.
Yeah.
Check. Smera got it. That is correct. I think there's a just check plus minus. Just get the calculations. Sanskriti, Sia, Kaveri, where you guys are?
Doing math.
That I'm like I already.
I'm almost done. I'm just checking my calculation.
Okay. Yeah. See, kind of done. Sia, what about you?
Actually, I got disconnected, so I couldn't see the question.
Okay. Now you got it. Arya, look at question 4. Sia, where are you? Sia has sent in. Yes, that is correct. Sia, do
Is the P total formula we can use for like the P naught 2 plus the brackets one?
Yeah.
That is we can use for solution also, like not only gaseous phase, right?
that is for solution.
Yeah. Oh, okay.
Raoult,
The other one is for gas.
yeah.
Yeah.
Ma'am, the PI and the P total wala formula, that is not pure, no?
No, don't like unless and until you're figuring out gas phase, do not consider that at all. As long as you're dealing with solution, like here, you have solution ka vapor pressure and concentration of the solution, and you need to figure out vapor pressure of pure B. So don't consider that at all. Like consider Raoult's law ka formula itself.
Okay.
Sanskriti, yeah, I got it. Yeah. So fourth is also pretty easy. It's just equimolar solution. Matlab, what is the question telling you? What is given? Just have to figure that out. But rest of it is pretty easy to get it. Yeah, Smera, yes. Okay, so these are the main different like types of questions you'll get on Raoult's law. Kaveri, that is question 3 ka answer, right?
Yes, ma'am.
हाँ, सही है. So question 4 is extremely easy. Like once you figure out equimolar solution kya hai, you get it. Sia, oh, just saw it. He also got it. तो संस्कृति no, that is benzene ka this thing. Check again. I think plus minus you must have like done something there. Cancel हुआ होगा. Figure it out. Check again. So यहाँ पे okay, another factor that you might have made a mistake. One is 160 and this is just 60. So check it. Smera and Sia have sent. Arya and Kaveri are yet to send. Sanskriti is correcting it.
Miss, can you solve the fourth one?
Okay. No, you'll be able to solve it. Okay. Like what all information are you given here then?
P naught D is 160. P naught T is 60.
A and B. A is benzene. B is toluene. Okay.
Yeah.
B is 60 mmHg. Okay. What else?
Equimolar meaning like the x1 is equal to x2.
Yeah. If x1 equal to x2, what values can they be? So chi A.
How do we know what values will be?
This is mole fraction. So if the number of moles of benzene equal to the number of moles of
1. So 0.5, 0.5.
Yeah. Yeah, that is it with. Like once you get it, it's pretty simple, direct. Sanskriti, were you like yahan tak did you get the same values?
Ma'am, I've taken all the values same, ma'am. Before I did some calculation.
So calculation देखना पड़ेगा. Addition, subtraction, multiplication. Yeah, Kaveri got it. Yeah, Arya, we got it.
Ma'am, is the answer 110?
Yes, 110 is the right answer. Okay, awesome. So these are like the main like different types of questions you'll get on this concept, Raoult's law. We like pretty much touched all different types of problems. One is variations of Raoult's law only. You saw that you have to find out like P naught of one of the components, or you have to find out the P total, or you need to find out the mole fraction. ये कुछ भी आ सकता है. And another major type of problem is solution है. You have to find out one of these anyway, and then you also have to figure out gaseous phase में क्या हो सकता है. These are the important types. Break. Okay, 4:56 आ रहा है, हो रहा है. So we'll resume at 5 o'clock. इसके बाद what else do we have? हाँ, ideal and non-ideal azeotropes is what we'll be talking about. That's the last concept for today. Okay, we'll meet at 5 o'clock again. Chalo. Okay, so one tiny thing that I missed out for liquid solutions or Raoult's law basically is what does Raoult's law state? Like from Raoult's law, what did we get?
Partial pressure is directly proportional to mole fraction.
Like a component, like suppose we have PA that is directly proportional to the mole fraction, or proportionality constant we got as the vapor pressure of that particular liquid, right? And what does this look like? Like, does this look familiar to you guys? कोई दूसरा formula है क्या in the similar thing, similar format?
is equal.
What was that, Arya?
KH is equal to.
KH equal to
Henry's law.
Henry's law. Yeah, like Henry's law का ये क्या है?
P equal to KH into mole fraction.
Is that only I said KH? Close.
You had the right idea. You didn't remember this thing. KH equal to nahi, but yeah, similar stuff. So in this case, we're talking about the solute, which is the gas. Partial pressure of that particular gas is directly proportional to, or as you increase the pressure above the solution, uska solubility, mole fraction will increase, right? So Raoult's law is applicable to liquid solutions, and this is applicable to gas in liquid solutions. So mathematically, both are very, very similar to each other. They just differ concept-wise because this is applied to liquid. That's why vapor pressure comes into picture. And this is applied to gas, and gases ka direct unka pressure is what we are talking about. Okay. So if you look at it mathematically, because it's equal, we can say Henry's law is a specific case of Raoult's law, जिसमें instead of a liquid, if the solute was a gas essentially. Okay, so the situation is like this. We talk about vapor pressure because liquid is evaporating into gas and they are in equilibrium. What if all of the liquid has evaporated into gaseous phase? Like what if there was no liquid phase at all? Okay, so that's where we get into Henry's law territory, where the gas is dissolving in liquid rather than dissolving two separate liquids.
We go from liquid to gas liquid.
Yeah.
That happens then?
No, this is again hypothetically, like because like numerically you can see that Raoult's law and Henry's law are very similar to each other, right? So we can consider Henry's law as a special case of Raoult's law. So Henry's law can be considered as a special case of Raoult's law, in which the vapor pressure is actually like when all of the liquid has evaporated into gas. Like instead of a liquid, if you have a gas. Yeah, Kaveri, what's up?
So Raoult's law can be like basically liquid can be made to gas liquid by increasing the temperature, right?
Increasing the temperature, also you need to ensure that solvent jo hai, that remains as liquid only. Usme
There has to be like a difference in the boiling point between the solute and the solvent.
Yeah, you need a large difference between the boiling points. Yeah. Okay. That is the thing. Like numerically, both are very similar, very close to each other. So that is why you can consider Raoult's law to be a special case of, Henry's law to be a special case of Raoult's law, essentially. Yeah. If KH value is equal to P naught, that will be the difference between Raoult's law and Henry's law, mainly. And so now let's talk about solid liquid solution. So solid liquid solution मतलब solids के case में vapor pressure नहीं होगा, and again we are not considering solids that are capable of sublimating. तो अगर solids sublimate हो रहे हैं, मतलब sublimation is what? Conversion of solid to gas, in which case volatile solid, again we can apply Raoult's law in that situation. All of that happens. So we're talking about non-volatile solids. So solid liquid solutions with non-volatile solids, or let's say non-volatile solute, क्योंकि solvent तो volatile ही होगा. So यहाँ पे solute is solid, nothing, there's no vapor pressure, there's no pressure, there's nothing we can apply to it in this particular context. But the solvent is a liquid, matlab uska vapor pressure hoga. In the case of solid liquid solutions, what do you think will happen?
Happen when?
Okay, let me put it in context. Okay, so in the case of liquid solutions, if you are mixing two liquids, vapor pressure is changing to somewhere between both of their vapor pressures, right? Like higher one ke liye it is getting lowered, and the lower one ke liye it is getting higher, like it's increasing. So the total vapor pressure of the solution is falling somewhere between P1 naught and P2 naught, उस range में. Now solid liquid solutions के लिए liquid का एक P naught होगा, like its own vapor pressure of the solvent, the liquid that's solvent. So what do you think will happen to this vapor pressure when you add a solute to it?
It'll decrease
Decrease, yes. Why?
because I don't know how to explain, but like the solute will be covering the the surface of the liquid. So
Absolutely, yes. So when it is a pure liquid, let's say this is the container, pure liquid hai. So this is pure liquid. So all these like evaporation will take place only for the surface molecules. So all these molecules are capable of evaporating out into this thing. Now isme if I suddenly add a solute dissolving matlab kya, it takes the place in between the solvent molecules, right? Niche pura it is covered, okay, we don't care about that. But surface maybe it's going to occupy the space in between the solvent molecules. Matlab it is decreasing the surface area of the solvent for evaporation. Matlab lesser number of molecules available for going into vapor phase, and lesser number of molecules matlab vapor pressure decreases. Decreases compared to the pure solvent. As some of the solute molecules are on the surface or occupy the space on the surface, and the number of solvent molecules available for evaporation is reduced. Number of molecules reduced matlab the vapor pressure also reduces. N decrease hua matlab P also decreases. PVA. So this like decreases by how much it decreases. So this decrease in vapor pressure only depends on the amount of solute and not on nature of solvent. It doesn't matter whether it's a volatile solvent or a less volatile solvent, it doesn't matter. By how much it decreases only depends on the amount of solute. ज़्यादा solute डाला तो ज़्यादा decrease होगा, If you put less number of solute molecules, then the decrease also will be tiny. So this further, like there are numericals related to it. There's like by how much the vapor pressure decreases and all that. So we'll study about this as a part of colligative properties. Because solid liquid solutions may, it's not just effect on vapor pressure, it also affects the boiling point, melting point, and all of these other things. So we'll study all of them together as a part of colligative properties. Okay. So yeah, Smira, I think you guys are done. Sanskriti, Kaveri, let me know when you also finish writing and we'll look at ideal, non-ideal.
I'm done.
Arya finished? Kaveri?
Just a second. Done.
So Raoult's law, the perfect graph, like theoretically based on all these relations, what we saw is, though liquids say if this is the partial pressure of one of them, this is the partial pressure of the other one. So solution ka vapor pressure ranges, like this is the graph that it comes out to. And equation se bhi we saw that it's a straight line, y equal to mx plus c format mein tha. Now, just like how we came across for as ideal gas equation ke liye, you have ideal gases, but reality may it's not ideal, it's non-ideal, right? That way solutions, maybe you have something called ideal solutions and non-ideal solutions. So ideal solutions versus non-ideal solutions. Can you guys figure out what would be categorized as ideal versus what would be categorized as non-ideal?
Ideal is like hypothetical, it doesn't actually happen.
Kind of, but yeah, we do have some ideal solutions in reality. But again, what is the, like, even if it is hypothetical, agar reality mein ideal nahi hai, why are they not ideal? Like, what is the point of difference between both of these? How do we figure if something is ideal solution or not ideal solution?
Ideal solution is
Like-
something that follows Raoult's law at like.
Smira, what were you saying?
I was saying that it might follow rules in like any condition. Like we usually say na that we want a specific temperature. What if ideal solutions don't want a specific temperature? At every temperature they are following the rules.
What rules are they following?
Like these only, like Raoult's law or Henry's law.
Both of you are correct. Kaveri is more correct. Not Henry's law. Henry's law apply only for gases and liquids, but yes. So ideal solutions follow Raoult's law. Simple, that's it. And non-ideal solutions don't follow Raoult's law. Okay, so what do we mean by follow Raoult's law, don't follow Raoult's law? If they follow Raoult's law, when you draw this graph, it's gonna look like this. If they don't follow Raoult's law, we won't get a straight line. We'll get like something different other than this. Okay, so some like, okay, so now we look at
What did you say about Henry's law? Like
Henry's
you
law.
said about-
So we use Henry's law. Henry's law applies only when we dissolve a gas in a liquid. So Raoult's law is for when we dissolve liquid in liquid because it deals with the vapor pressures of the liquid.
But the ideal solution cannot be gas and liquid. Like that's still a solution.
That is still a solution, yes. We look at ideal solutions, non-ideal solution. These are different categories of liquid-liquid solutions. We look at specifically Raoult's law. When you dissolve gas in liquid, usme it is fixed what is solute, what is solvent. It's not like a mixture. You know that solvent you're taking a liquid or usme you're putting like a certain quantity of a gas. But when it comes to liquid-liquid solutions, like you did some examples, right? You take benzene toluene. So if you're mixing benzene in toluene, you can also mix toluene in benzene. Like the um, the concentration is going both ends of the spectrum.
Yeah.
So we're talking in terms of components and mole fractions rather than solute, solvent, or molarity and all that. So,
Yeah.
Okay, so a few more, like let's look at ideal solutions only. Like this is the basic definition you can say. Like you can define ideal solutions. If they follow Raoult's law, it comes under ideal solutions. And Smera, you were saying temperature, right? So it's instead of looking at temperature, again, things change once the temperature changes because the partial pressure is gonna change. Everything changes, right? That's why we define it for a specific temperature. But this variation, this relation, it needs to be a straight line across this whole spectrum. So we say follow Raoult's law across or over an entire range of what happened to my spelling? Range of concentrations. So ऐसा नहीं होना चाहिए कि lower concentrations में ही like where extremely dilute solutions follow the rare, but like other times it's not following it. Shouldn't be like that. So over the entire range of concentrations. So ideal solutions are those solutions that follow Raoult's law over an entire range of concentrations. And some criteria of Raoult's law or characteristics, you can say, what is observed with ideal solutions is that the delta H of the mixture. So basically, when you mix both of them, change in enthalpy should be 0. So it shouldn't be an exothermic or endothermic. So acid bases dissociation ho raha hai, and heat is acid bases. Sorry, when you're diluting acids, when you put acids in, when you mix acids with in water or bases in water, there is some amount of heat being released, right? That's why they say you should be careful when you're mixing and put acid in water and put only small concentrations. So that is most definitely not an ideal solution. Okay. So ideal solutions, delta H, like you shouldn't have any energy released or absorbed. And the delta V of the mixture. So overall volume also should not change. So if I mix 100 ml of liquid 1 and 50 ml of liquid 2, my total volume should be 100 plus 50, 150. It should not come to 151, 152, or it should not be 148, 149. So delta V of the mixture also should be 0. Delta H of the mixture also should be 0. Okay. And when it comes to non-ideal solutions, it's been observed that they are exothermic, endothermic. So like delta H of mixture is not equal to 0, and delta V of the mixture is not equal to 0. Now, why does the volume change? Like, why do we have non-ideal solutions? How come volume is changing? How come it's expanding or contracting? So let's say we are mixing two substances A and B. Okay. So at the molecular level, you have A molecules interacting with A molecules, AA interactions. And you have B molecules interacting with other B molecules, BB interactions. अभी mix करने के बाद A molecules and B molecules also interact with each other. So you have these three types of interactions. Now, when do we come across ideal versus non-ideal? Suppose AB interactions are the same as what you had with AA interactions and BB interactions. Like at a molecular level, if the intermolecular forces, how much they attract, how much they repel, all of that remains the same. If everything is comparable, then you end up with an ideal solution. But if AB interactions after mixing is different from the individual AA and BB interactions, if it's not the same, then you end up with a non-ideal solution. Now, what do we mean by AB interactions not being the same as AA and BB? Okay. So we'll get into that. Like, let me know when you guys finish writing. Once you, like, if you followed till here, let me know. Otherwise, I'll discuss this some more. Okay. Arya, Sia, Kaveri.
Done.
Okay. So I'll take some examples for these, like for non-ideal solutions. All right. So case 1, let's take mixture of benzene plus toluene. So benzene का structure, it's a 6-member carbon chain, resonance है. Toluene is also pretty much the same, 6-member carbon aromatic chain, resonance hai, and there's an extra CH3 there. Okay, so before mixing, benzene ke sare molecules are like this. So resonance, see, what do you guys know of resonance? You have like pi electrons ka delocalization above and below the ring, right? So interactions between two benzene molecules will depend on, repulsions of these negative charges, attractions due to, the molecular mass, van der Waals forces and all that. Interactions between two toluene molecules are also pretty much going to be the same. उनके पास भी same resonance pi electrons है, repulsions due to those electrons, due to those negative charges. Attractions, intermolecular attractions तो रहेंगे ही. When you mix benzene and toluene, will there be a difference in the interaction between a benzene and a toluene molecule, or will it pretty much be the same? It's kind of going to be the same because molecular masses are comparable, like only one CH3 का difference है. In terms of structural component also, दोनों के पास same resonance ही है. So benzene and toluene are an example of ideal solution. When you mix them, close to ideal. Like they will obey Raoult's law because the interactions between the individual molecules, between two benzene molecules, between two toluene molecules, and between one benzene and a toluene molecule are pretty much the same, the attractions, repulsions. So when it's escaping out in the atmosphere also, like the rate of evaporation is going to be the same. So the vapor pressure overall also, it's going to be as expected. Now let's look at a different case. If we mix acetone plus benzene. So acetone, you have CH3, C double bond O CH3. Benzene, you have ring structure. So benzene के पास, you'll have certain attractions, repulsions. Two acetone molecules, you'll have certain attractions and repulsions. But when you mix both of these, the interaction between acetone and benzene, अभी oxygen के पास lone pair of electrons है, and you have like double bond electrons. Now benzene के पास you have like this whole resonance thing going on ऊपर नीचे. Like यहाँ पे पूरा electron density है, यहाँ पे electron density है. So in this case, if we say this is molecule A and this is molecule B, the AB interactions, the interaction between both of these, or the attractive forces between both of these, are going to be weaker than AA or BB, like individual ones, when they were not mixed. These two are going to repel each other more than, like the repulsive forces between both of these would be more than if you had pure benzene or pure acetone. Making sense? Arya, no? It's all like compare the attractive or repulsive forces in all these cases. Okay. ये वाला केस समझ में आ गया, like why this would be ideal? यहाँ पे whatever attraction or repulsion you have between individual benzene molecules, that is AA,
Yeah.
is pretty much equal to, like AA and individual BB is pretty much equal to whatever interaction you have between a benzene and a toluene molecule. Because structures same hai, same resonance, same number of electrons are in resonance. So whatever repulsion you have will be the same. Molecular mass also very, very similar. Very small change in the molecular mass. So that way the van der Waals forces are also going to be pretty much the same between both. But acetone benzene में this is completely non-polar. यहाँ पे थोड़ा सा polarity है, lone pair of electrons है. So acetone plus benzene, the AA and BB are going to be like the interaction between AB is weaker than AA and BB. So weaker matlab the molecules are going to be slightly repelling each other more than if you had pure A or pure B.
Just what would how would the interaction between A and B in the second case take place? Like
When you mix them.
no, like you said that, ma'am, obviously when you mix them, but in the first case, you said that the interaction would be almost equal to the individual components because the structures are similar and so same resonance, similar van der Waals forces because. So how would like acetone and benzene basically react?
They would slightly repel each other. You have like lots of negative charges here, and like the
Some
repulsion will
resonance.
be more than if you had individual, like the repulsion between AB is more than the repulsion in AA or repulsion in individual BB.
The basically the electrons that are in resonance in benzene would repel the free electrons on acetone ka O.
Yeah.
Ma'am,
Yeah.
my brain has like stopped working.
Okay. At till what point did you are you able to get, like, where did it just go whoosh? At what point?
This case I didn't understand at all.
This you got the hang of it.
Yeah.
Okay, so this case, right? So if we're just comparing interactions, kaise rahega? Like when it is purely benzene, it is of one type. Like there's going to be attractive forces, it's going to be repulsive forces. When it is purely acetone also, they'll have their own set of attractive forces, repulsive forces, jo bhi hai. When you mix acetone and benzene, mixture hai, then these two are forced to interact with each other. The molecules are mixed. They will hit each other. Now, the mixture may, we are looking at what their interaction is going to be compared to if you had purely A or purely B. If it is comparable, like if AA and BB are same as AB, like jitne attractive forces, jitne repulsive forces hai, if it is pretty much the same thing, their ability to vaporize also will pretty much remain the same. But if it is different, like अगर attraction ज़्यादा है या फिर repulsion ज़्यादा है, then it's going to affect. That's what we are looking at here. Or instead of this, let me take another one that will be more intuitive. Case 3. Take any acid. Let's take HCl plus water. What happens when you add acid in water? Like you have studied acid bases, 10th tak you've done reactions and all also, right? So what happens when you add acid in water?
Dissociation.
Dissociation takes place. Then what else happens? Last time, like last year, equilibrium में you guys studied, no? ये dissociate होने के बाद, can H plus remain independent?
H hydronium ion.
Hydronium ion. So like immediately the water molecules And then you guys also studied about solvation, like hydration, where the water molecules surround the ions. No? Yes? Not familiar?
I don't remember.
Hydration, guys. What is the reason lithium ka this thing, like even though it's small, why is it extremely reducing? It has extremely high hydration energy, like it, like lot of water molecules around it. Basically, this is what happens in solution when you put ions, like whenever you dissolve any salt, dissociation takes place. Like even when you put sodium chloride or something, dissociation takes place, you have the cation, anion. Immediately those ions are surrounded by water molecules. So that's hydration. If you have Na plus, positive ion hai, so it's surrounded like this direction, all the negative side of water like gets around it. And if you have a negative ion, like if you had a chloride ion, it's going to look something like this. So water is polar, the positive side is going to surround it, basically. Okay, so this is like the phenomenon of hydration definitely always takes place. Any ion dissociation ke baad, the water molecules surround it, like they're attracted to that opposite pole, essentially. Okay, so once you know that that happens, hydronium ion hai, and you have chloride ion also, which is like surrounded by water molecules, like this is also like hydrated. In this case, what can you say about the interactions? Like if you compare, like again, this is A and this is B. AB interactions, would you say are stronger or weaker than AA and AB? Like the individual attractions? Like are they interacting more? Like are they attracted to each other more, or are they attracted to each other less, or is it pretty much the same thing?
Pretty much the same. Because the H, when HCl and H2 are reacting.
Think of when you had only HCl. थोड़ा सा hydrogen bonding रहेगा, but that's about it. And compare it with like individual HCl के बीच में जो है, compare it with when it is dissolved in water. Is it stronger or weaker? Stronger, na? What else?
How stronger?
Why stronger?
Because there's hydration taking place. यहाँ पे you just have like the general interaction between polar molecules जो है. That's basically it. But when you're mixing both of them, dissociation is taking place. You have hydronium ion being formed. A lot of chemical changes, stronger interactions. Water basically completely dissolves this acid.
But how is it stronger than individually water reaction and HCl?
Because individually you don't have all these things. Like how can it like why do you think it is comparable? Like why do you think it is not stronger?
Because the bond in between similar molecules will always be more as compared to when you mix two different, right?
Not necessarily. Why should it be always the strongest? if that is always the strongest, then you can never have things mixing with each other. For chemical reactions taking place, all of that gets difficult because then you'll have to give it extra energy if that was the case. Okay. But essentially, this is the concept. So it all depends on individual interactions versus interactions in a mixture. If AB interactions are stronger, like if A and B attract each other more than if they were individual AA and BB, or if they're attracting each other less, if they were repelling each other compared to AA and BB, then you get non-ideal solutions. Okay, so within non-ideal solutions, depending on whether it's like case 2 or case 3, whether these interactions are weaker or stronger, you have something called positive deviations and negative deviations. Okay, so non-ideal solutions.
Stop now.
It's getting a little too heavy. Okay, it's just a tiny bit. Like again, this all basically theory. So once you know that there are non-ideal this thing. So within non-ideal solutions, so if interactions between AB are stronger than the individual interactions, AA and BB, then you get stronger attract chloride and you get negative deviation. So negative deviation, matlab again, because it's negative deviation, if ideally if this was the case, the actual values, let's put this dotted line, kyunki ideally if this was the case, because of stronger interactions, the real values are lower than expected. So this is the graph for P total. If it followed Raoult's law, straight line hona chahiye tha. But because it's not the ideal case, how they deviate from Raoult's law is, it is the values of P total are lesser than expected. And why are they lesser? Now, A and B interactions are stronger, right? So if it was just left as pure components A and B, then certain quantity of them goes into the vapor phase. But mix karne ke baad, B is holding on to A tighter and A is holding on to B tighter because these interactions are stronger. B is able to hold on to A molecules better than A molecule was holding on to another A molecule.
Ma'am.
Yeah?
I can't.
Not getting it. Okay, it's all like 10 minutes to 6, right? Okay. So next
I
time.
didn't understand why it's negative.
Yeah, stop.
Okay, that's what we were just discussing. Like we were in the middle of that. Okay, so next class kab hai? Kal hi hai na? Another last class of solutions. Okay, so we'll pick up from non-ideal solutions then more on this.
How much of the chapter